and today we'll be covering optimal design methods utilizing RecurDyn's optimization toolkit AutoDesign. This is the itinerary of this session today. First, let me explain about optimal design. What is the optimal design? I define optimal design as a design that fulfills the design objectives while achieving the desired performance. For example, when designing a product, if you need to create a lightweight yet sturdy product, lightweight would be the design objective and sturdy would be the performance criterion. The question then becomes how to design a product that is lightweight enough while still possessing the desired stiffness. Finding the solution to this problem is what we call optimal design. Depending on the type of optimum point we are seeking, there are two optimization methods: deterministic optimization and robust optimization. As shown in the diagram, deterministic optimization finds the best point in terms of performance, but it does not consider variations in design variables, which can lead to significant performance variations depending on the deviation of the design variables. On the other hand, robust optimization takes into account the deviation of design variables while finding the optimal point. In reality, it is impossible to manufacture a design with exact dimensions without any errors. Therefore, designs are usually created with some tolerance in mind. Robust optimization aims to find the optimal point considering the tolerance of design variables. If you desire a stable design despite manufacturing tolerance, it is preferable to find point B in the diagram here. Thus, it is important to determine which optimization approach is the most suitable for a given problem. If that's the case, why do we need an optimal design? Intuitively, we can think of the process on the left to find the optimal design. After conducting the design, we create a prototype for design verification and proceed with the testing. If your desired performance is achieved, we move on to the process of creating the final product. However, if there are issues with the design, we'll have to modify and repeat the process of verifying the design. However, using such a process makes it difficult to understand how design variables affect performance, leading to numerous try-and-error iterations of design modifications and verifications. On the other hand, by pursuing the optimal design, a more efficient approach becomes possible. First, we formalize the design problem by defining design variables, design objectives, and performance indices. Then, to understand the relationship between design variables and performance indices, we conduct experiments on several designs. The method of constructing experiments for performance evaluation is called design of experiment. Finally, by analyzing the results of the experiments, we identify the relationship between design variables and performance indices, ultimately deriving the optimal design variables. By following this process, we can find the optimal design more efficiently and also identify potential issues that were not anticipated in the early stages of the design. Now let me explain how this can be applied to a practical design problem through a simple example. Let us apply the optimization to the problems that we might encounter in our daily lives to make this session more relatable for you. In this video on the left, You might see a situation that might seem funny to you, but it is quite unfortunate for the person involved. As you can see, the table collapsed after two people sit on one side of the table because it cannot support their weight. Could this problem have been prevented through better design? Let's try applying the process that I mentioned earlier to this example. First, we should determine the design variables. Design variables are the values that can be changed within the design. Since the design of the table surface is fixed in this example, we want to try to change other aspects of the design. Therefore, we define 6 visual values as design variables. Next, let us define the design objectives. Design objectives are the problems we want to solve through design modifications. In order to prevent accidents like this one shown in the video, the first design objective could be to ensure that the table remains stable even under an unbalanced load. Additionally, we aim to use minimal materials for cost effectiveness. The performance indices are the experiment results that allow us to assess whether the design objectives have been achieved. To evaluate the unbalanced load, we defined the ground reaction force on the table legs as a performance index. We also defined the length of the material to determine the amount of material we used. This is represented more specifically in the table on the right. Since we cannot consider all possible values for the design variables, we need to define lower and upper bounds for each design variable. We also provide specific requirements and goals for the performance indices. By utilizing the previously defined information on design variables, we can consider various design options. Evaluating the design for all possible cases would be ideal, but due to economic or time constraints, it is advantageous to analyze the design with as few experiments as possible. This is where the design of an experiment comes into play. Through the design of an experiment, we can design experiments and measure the performance indices for each design option. Finally, by analyzing the results of the experiments, we can identify the relationship between design variables and performance indices, enabling us to find the optimal design variables. Although briefly described in words, actually going through this process is not easy. Even planning the experiments can be challenging as it requires background knowledge to apply the design of the experiment. There are also challenges in analyzing the experimental result to derive the optimal design. To address these challenges, our design can be utilized. AutoDesign automates all steps of the design process except for formalizing the design problems, resulting in derivation of optimal design values. On the next page, before explaining AutoDesign, I'll first describe how to create a RecurDyn model for the table problem. First, let me introduce parameter modeling. To automatically perform simulations according to various design options, we need to make the model change based on the design variables. In RecurDyn, this is called parametric modeling, and it can be implemented using parametric values and parametric points. PV stands for parametric value. This value can be defined as a constant or as a mathematical expression. PVs can be specified as design variables as well. PP stands for parametric point. You can input x, y, z values. You can input some or all of the coordinate values as a PV. For example, the point 300, 200, 0 can be inputted as PV1, 200, 0. In this case, PV1 must be defined in advance. It can be also set by changing the origin of the coordinate system. Press the F button next to the Relative to option and select a coordinate system. The default state is unselected, which means the global coordinate system is being used. PVC stands for Parametric Value Connector. In RecurDyn models, the top-level environment is called assembly mode. PVCs connect PVs defined in the top-level environment with the PVs defined in the body edit mode or subsystems. By doing so, you can set it up in a way that when the PVs in the assembly mode are changed, the PV values in the lower level environment also change accordingly. PPC stands for Parametric Point Connector. Similar in concept to PVC, it connects the top-level environment PP with the lower-level PP. The way to set up PPC is the same as PVC. Using these functions I just mentioned, let us work through a parametric model. In assembly mode, create a parametric value. In this video, we set the input as the constant value of 500, but we can also use the expressions for PV. After creating this, we can check the parametric value we created in the database. We want to make the cylinder's length change depending on the PV. First, let us create the cylinder. Enter the body edit mode of the created cylinder and create PVs and PPs. Open the Properties dialog box of the cylinder and change the coordinates of the second point to the PP you created. In this video, the PP was connected after the cylinder was created. It is also possible to reverse the order by creating the PP first and then utilizing the PP when creating the body. Exit body edit mode and return to assembly mode again. To connect the PVs defined in the body edit mode and assembly mode, let us create a PVC. In the value item, select the PV in assembly mode. After that, press the reference button and select the PVs that are referenced. Once the creation of a PVC is complete, we can see that the length changes of the cylinder according to the PV value defined in assembly mode as follows. By applying the information given in the previous slides, you can create a model whose design changes according to the input values. The overall design of the table does not change, and the design of the legs, such as the location and length, is changed according to the 6 variables shown in the figure. In addition, to simplify the example model, the material, which is a rectangular piece of wood, as shown in the figure, is assumed to be a cylinder shape. If you want to look at a more complex example, a new approach is possible with the new features released in RecurDyn 2023. After defining the point information that composes the outline using PP and PV, create a solid shape using the fill and extrude functions. Here, the outline which was used to create solid changes based on the value of PP. This also changes the dimensions of the solid created automatically. Parametric modeling can be applied even to more complex designs by utilizing this. Now, I'll move on to talk more about AutoDesign's usages in detail. As mentioned before, if users can formulate the design problems, even complex modelings can be solved easily by utilizing AutoDesign. AutoDesign automates the entire process, including design of experiments, simulations, and deriving the optimal design solution using design of experiment. Therefore, even users without background knowledge of optimizations can solve problems easily. Let's use AutoDesign to solve the table problem that was introduced earlier. First, define the design variables. If you press the parameter button, the following dialog box will open. Press the Create button and add the design parameter you'd like. We will set this parameter to the PV that we previously chose. The design variable's current value will change to the PV's current value. Users then can choose the lower and upper bound on the value. Specify the 6 PVs of the table model created using parametric modeling as variables according to the process previously described. Once you are done defining the design variables, you will see the 6 different design parameters inputted as seen in this image. Next is defining the analysis response. Specify the item to be analyzed among the simulation results. The analysis response is defined using expression. Additionally, since the analysis results are not a single value, but values over time, you need to specify which result within the interval should be considered as the response value. For example, if a treatment is set to max value, the maximum value among the analysis result is specified as the response value. You can also set it to maximum value, average value, standard deviation, and more. Following the previous explanation, we will designate the performance indices of the model as the analysis responses. For the ground contact force, we define it as an expression that represents the result of the contact. For the length of the material, we define it as an expression that calculates the distance between markers. Thus, we have defined these 4 performance indices as the analysis responses. Additionally, I have added here 2 more performance indices. The reason for this is to impose constraints on the distance between the chair and the table, which should be suitable for a person to sit comfortably and the height of the chair. Now, let us configure the optimization settings using the defined design variables and analysis responses set earlier. By clicking on the optimization icon labeled Opt, you can perform deterministic optimization. In the first step, the design variables will be displayed, which were previously entered in the parameter menu. You can set the type of each design variable as either variable or constant. If you set it as a variable, the optimization process will consider that value as a variable within the specified boundary conditions aiming to find the optimal value within those boundaries. If you set it as constant, the optimization processor will treat that value as the fixed value specified in the value field during optimization. Since the goal in this example is to find the optimal values for all the entered design variables, set them all as variables and proceed to the next step. Next is the parameter index step. In this section, set the performance indices to determine the optimization. Clicking the Add button will add an entry to the list. Then, click the small arrow button next to the AR item, and you will see a combo box listing the responses you defined earlier. You can select the desired analysis response as the AR. The definition field can be set as either objective or constraint. When definition is set as objective, you can select either minimum or max. When set to max, it means that the purpose of optimal design is to maximize the value of the specified analysis response. For constraint, define it as either an equality or inequality condition. For example, if you set it as LE less than or equal to, it means the optimization aims to achieve the specified analysis response value less than or equal to the limit value you entered. Set the analysis responses as performance indices as you see here. Include the 4 performance indices defined in the formulation process, along with the 2 additional performance indices. In total, you have entered the 6 performance indices. With this, all the necessary design information for optimization has been entered. Before defining the optimization-related settings, let me explain the process of optimization in AutoDesign. In the DOE phase, the simulation is performed for predetermined cases based on the DOE method. The number of simulations to be performed in the DOE phase can be determined before the entire process is executed. Once the DOE phase is completed, a meta model, which is a surrogate model of the actual model, is created using the DOE results. The created meta model is then used for SAO, surrogate assisted optimization. SAO involves the iterative analysis using the meta model to find the optimal values. In the SAO phase, the meta model is used to derive the optimal design values. The analysis is performed for these values, and the performance indices are evaluated. If the results do not meet the objectives, a different optimal value is derived from the meta model. This process is repeated until the results are deemed suitable for the given objectives, at which point it is considered the optimal value and SAO is concluded. The difference between AutoDesign and other optimization programs lies in the fact that AutoDesign does not continuously use the meta model derived from the initial DOE results. Instead, AutoDesign updates the meta model by incorporating the results obtained during the SAO process into the initial DOE results. This allows AutoDesign to achieve optimal results with fewer experiments compared to other optimization software. For example, there was a case where AutoDesign solved a large optimization problem with 105 design variables and 14 analysis responses using 109 initial DOE runs and 7 SAO iterations, totaling 116 analyses. Next, let me proceed with the settings for optimization. By clicking the buttons for DOE and Meta Model, link method at the top, a dialog box will open where you can choose the methods for generating the DOE table and creating the meta model. In most cases, it is recommended to use the default option Auto Selection. However, for detailed information about each algorithm, please refer to the manual. Next, we have the Convergence Tolerance section. These values represent the tolerance for determining convergence during the optimization process. Convergence is deemed to occur when the error is smaller than the specified tolerance. Depending on the convergence of the problem, users can adjust the tolerance values. The objective change rate is the tolerance for the performance indices defined as objective functions. The equality constraint and inequality constraint represent the tolerance for the PI defined as constraint. EQ for equality constraint, LEGE for inequality constraint. The maximum iteration of SAO refers to the maximum number of iterations for SAO. If convergence is not achieved within the default 50 iterations, you can consider increasing the number of iterations and performing the optimization again. The convergence relaxation control is an option that automatically adjusts the tolerance as mentioned earlier. By default, it is set to off. If you set it to on, the AutoDesign server will adjust the tolerance to facilitate convergence during optimization. Although there may be some deviation from the optimal value due to adjusting the tolerance. For models that take a long time to analyze, using on can reduce the number of iterative analysis and find an approximate optimal value more quickly. The simulation type can be selected as either dynamic or static. When using the Save Result option, the result file name will be outputted with the name you enter in the blank field. The number of trials indicates the initial number of experiments generated by DOE. When clicking the Analysis Setting button, the Properties dialog box for the selected simulation type will appear as follows. Now that the setup is complete, click the Execution button. In the dialog box that appears, you can review the information you entered. After confirming that every information is correct, click the OK button to start the iterative analysis for optimization. Since the Display Animation option is checked in the Analysis Settings dialog box, you can observe the animation while the simulations are performed. As you can see, the model undergoes changes while performing the iterative simulations during the optimization process. Once the process is complete, the result dialog box will appear. At the top of the result sheet, you can find the results for the SAO iterations. The top section displays the AR results for each SAO iteration. Additionally, in the plot window below, you can observe the convergence process during the SAO iterations. The summary sheet provides information about the results of optimization. It allows you to review the optimal design variables and their corresponding analysis responses. You can also review the definitions of performance indices. In the SAO section at the bottom, the number displayed for initial sample run represents the number of DOE runs conducted for the initial meta model generation. The SAO run indicates the number of SAO iterations. The number in parentheses indicate the count of duplicate design variables encountered during the SAO iterations. You can think of it as taking the same path multiple times before reaching the optimal point. If the same SAO case is encountered, that case is not simulated again since the results are already available. Finally, by clicking the Create New Optimal Model button at the bottom, you can generate a new RecurDyn model file with the applied optimal design variables. The Apply to Current Model button applies the derived optimal design variables to the existing model. This compares the initial design and the derived optimal design results. In the situation where a load of 200 kg is applied to one side of the chair as seen in the animation, the initial design topples due to the unbalanced weight. However, the table that underwent the optimization process remains stable and does not topple under the same situation. Next, I will explain the method for robust optimization. The parameter and response are the same as previously explained. When you click on the robust icon at the top, a window for performing robust optimization will open. It is similar to deterministic optimization, but with a slight difference. Since robust optimization considers the deviation of design variables, you need to input information related to this. In the statistical info section, you can choose between random or deterministic. If you choose random, you define the design variables with values that have variations. If you choose deterministic, you define the design variables with the values without variations. The deviation type is an option that determines how the deviations are applied. If you set it to SD, standard deviation, the value entered in the dev value field is directly applied as the deviation. If you set it to curve, coefficient of variation, the deviation is applied as a ratio. The deviation is calculated as the product of the deviation and the value entered in the depth value field. This allows the deviation to be applied differently depending on the design variable. Generally, when the design variable is of a constant type, you define the deviation using curve. This is the section for entering the performance index. The way weight, limit, robust index, and alpha weight are applied differs depending on whether the performance index is defined as an objective function or a constraint. In this case, setting the robust index to 6 means the commonly known 6 sigma condition. Next is the Optimization Control tab. Except for the DFSS, Robust Design Control section, the settings are the same as in deterministic mode. Here, DFSS refers to Design for Six Sigma. This setting is an option for a process that users can selectively perform. During the optimization process, when calculating the standard deviation, a meta model is used. The DFSS option allows the validation of the meta model by comparing the standard deviation obtained from the meta model with the standard deviation obtained from the actual model. The default value is none, which means this procedure is not performed. If it is set to value other than none, Additional analysis for validation are performed for the number of sample points specified in sample point for validation, in addition to the SAO process. Therefore, it is recommended to keep the default value of none unless necessary. Next is the result sheet description. In the robust mode as well, when the optimization is completed, a dialog box showing the results of the SAO process appears. The difference is the addition of a standard deviation and robust index. The standard deviation shows the standard deviation of the analysis response. The estimated STD is the result calculated using the meta model, while the sampled STD is the result calculated using the actual model. In this example, since the design control option was set to none for validation, the sampled STD values are all shown as 0. In the robust index, the user-defined value is the value input by the user, and the relaxed value is the robust index value applied to the final converged model. If there is no design variables that satisfy the performance index within the input range of the specified deviation in AutoDesign, the robust index is adjusted to proceed with the optimization. Therefore, there may be slight differences between the user-defined robust index and the robust index applied to the optimal model. In such cases, confirm the user-defined value and relaxed value in the dialog box. In this example, since the user-defined robust index and the relaxed value are the same, it indicates that design variables that satisfy the Six Sigma requirement for all performance indices have been found. The summary sheet also provides information the same as the deterministic optimization in addition to displaying the values mentioned earlier. When comparing the robust design result to the initial design, we can observe that it remains stable and does not topple even under biased roads. So what are the differences between the deterministic results and the robust results? Upon reviewing the design results, the following observation can be made. In the initial design, the position of the bridge supporting the load is noticeably more inward compared to the position of the chair where the load is acting. As a result, under heavy loads, the table is prone to tipping over. In contrast, the optimal design shows an improvement in addressing this issue. Furthermore, when comparing the deterministic and robust results, the robust design appears more stable due to the supporting point being positioned further inward compared to the supporting structure. This indicates that the robust design aims to achieve stability even in the presence of design errors in factors such as the length of the bridge or the length of the chair. While these results may seem obvious, they highlight the importance of considering and addressing design vulnerabilities. As you can see, such design issues are prevalent in real-life situations. Next time you see a table like this, recall today's lesson and exercise caution. Today, we discussed a relatively light problem, and I believe that conducting an AutoDesign tutorial based on this content would help you understand it better. I encourage you to also challenge yourself with optimization using AutoDesign. Thank you.